7.6 arc length. Sometimes we want to find the length along a curve, and we use the Pythagorean theorem to approximate it. One way that we can do it is using the Pythagorean theorem to approximate it. And so I have a curve here, and this distance here is 0.5. This distance here is 0.5. This distance here is 0.5. And if we start looking at this as, this is your triangle, this distance here is going to be 4 minus 3.125, so that's going to be 0.875. And then similarly here, this is going to be 0.625. It's going to be 3.125 minus 2.5. And then we can calculate this hypotenuse. Then this distance right here is the 2.5 minus 2.125. And we would calculate the hypotenuse. So you can see how we can inch along and calculate that and add it to that and add it to that. And we'll have an approximation for the arc length of the curve. So I'm just going to list all of our values here. So from 0 to 1/2, if I was calculating that hypotenuse, 0.5 squared plus 0.875 squared. And then from 1/2 to 1, square root of 0.5 squared plus 0.625 squared. From 1 to 1.5, square root of 0.5 squared plus, this one is 0.375 squared. From 1.5 to 2, square root of 0.5 squared plus 0.125 squared. From 2 to 2.5, square root of 0.5 squared plus another 0.125 squared. And then the last one, 2.5 to 3, square root of 0.5 squared plus 0.375 squared. So we're going to calculate those values, and we're going to add them up. So the first one should have given us 1.00778, and then we have from 1/2 to 1, and that should have given us 0.80039. From 1 to 1.5 should have been 0.625. From 1.5 to 2, 0.51539. 2 to 2.5, 0.51539, and 2.5 to 3, 0.625. And if we sum all those up, we can say that the arc length from 0 to 3 along that curve is 4.08895 approximately, because of course there was a little bit of error there. So we like to find the exact length though, of course, so there is a formula for that. So suppose f is a smooth curve on the interval AB. Find the arc length L of the curve, y equals f of x over the interval. And so the arc length L on the interval AB, where a comma f of a and b comma f of b are endpoints. A smooth function f is smooth on an interval if it has a derivative f prime that is continuous throughout the interval. So we're going to try and figure out what this formula would be. So we're going to just draw a random curve and we're going to say goes from A to B. And any point along here, we could think of this as our change in the length of the curve, and think of it as a little triangle here. This would be our change in x and our change in y. And we know that dx is the same, can be substituted for delta x, and similarly dy can be substituted for delta y, and that dl could be substituted for delta L. And so if I wanted to solve for my dl, I could take the square root of both sides. Dx squared plus dy squared equals dl. And if we took the limit as delta x goes to 0 and delta y goes to 0 of the square root of dx squared plus dy squared, we could see that our L, which is our arc length, is going to be the interval or the integral of dl. So our L is going to be the integral of the square root of dx squared plus dy squared, integral of the square root of dx squared times, now, well, think about what I just did here. If I factored dx squared out of here, out of this 2, I get 1 plus, and then I would take my dy squared and divide it by that dx squared. So I basically just factored dx squared out of this binomial. And so this is dx squared times 1 plus, and we could write this as dy dx squared. And the square root of dx can become, it can come out of there because the square root and the square go away. And that comes out like that. So if we wanted to find the length along the curve from A to B, this is going to be our formula. Now, if you have a curve that's defined as a function of x with respect to y, you also could look at the length along the curve from C to D, where C and D are y values. And this would be the square root of 1 plus, and then this would be dx dy squared, dy. So everything would be in terms of y there. So either one of these, depending on if you have your function in terms of x or if you have it in terms of y. So let's look at an example. Find the length of the curve over the interval from 0 to 1. So we have L equals the integral from 0 to 1, square root of 1 plus. Now over to the side, we're going to find f prime of x. And for this function, if I bring my 3 halves down, my 3's are going to cancel, and my 2 also cancels with one of the 2's in the 4. And we have that, which you could also write as 2 times the square root of 2x. And so 2 times the square root of 2x, the 2 and the x are in the denominator, squared dx So integral from 0 to 1, square root of 1 plus, and this would be 4 times 2x dx. Integral from 0 to 1, square root of 1 plus 8x dx. And then I would use my u substitution, and my du would be 8 dx. So du over 8 is my dx. And you don't want to put these in because we're changing it to a u. And so we want to find out if our x is 0, what is our u? And it would be 1. If our x is 1, what is our u? And it would be 9. So this would be 1 to 9, and I won't put my stuff back in. I won't put my 1 plus 8x back in. I'm using u now. So this is going to be 1/2 plus 2/2, which would be 3/2, and then multiplication by 2/3 from 1 to 9. And so divide by 2, we've got 1/12, and this would be the square root of 9 cubed minus, and let's just go ahead and put a bracket there, square root of 1 cubed. So 1/12 times, this would be 3 cubed, which is 27 minus 1, 26/12, which can be reduced to 13/6. And that's what the answer is for that example number 1. Example number 2, some of these integrals are a little tricky, but once you get used to them, they won't be bad. This example number 2, I had a little bit of trouble fitting it on my paper, so I'm going to try and write small. Integral from 0 to 3, square root of 1 plus, and now we need to find our derivative here. And so we would bring our 3/2 down times 2/3 would give us 1. X squared plus 1 to the 3/2 minus 2/2, so that's to the 1/2 times the derivative of that. So our derivative is going to be 2x times the square root of x squared plus 1. So this would be 2x times the square root of x squared plus 1 quantity squared dx. Integral from 0 to 3, square root of 1 plus 4x squared times x squared plus 1 dx. Integral from 0 to 3, square root of 1 plus 4x to the 4th plus 4x squared dx. And then you want to put that so that it has its highest down to its lowest, because this is going to be a perfect square. It's going to be 2x plus 1, or 2x squared plus 1 squared. And so then the square root and the square go away. And so I'm actually integrating just 2x squared plus 1 dx. Or no, I don't want to do that. I want to go ahead and integrate. Sorry. So this is going to be 2/3 x to the 3rd plus x from 0 to 3. So 2/3 times 3 to the 3rd plus 3 minus, that's always all going to be 0. So we've got 9 times 2 is 18 plus 3, 21. And that is the answer to example number 2, 21. Luckily, number 3, we can use a calculator. So when there's a calculator there, you just want to set it up correctly. And so we've got the integral from 1 to 8, square root of 1 plus, and then we had to find our y prime. Bring the 2/3 down times the 2/3, gives you 4/9, x to the 2/3 minus 3/3, which would be x to the negative 1/3, So I went ahead and wrote that as 4 over 9 x to the 1/3 squared dx. And then put that in your calculator. Looks like I did one more thing. I did 16 over 81 x to the 2/3. And then put it in my calculator, but you might want to just put it in your calculator from the get-go. Just in case you make a mistake. You don't want to make that mistake. Going from here to here and then getting this answer wrong. All right, example number 4. Find the length of the curve, and look, you've got y values. So this is going to be one of those where if you're going from 2 to 3, that this is going to be dx dy or x prime. And so for that one, I got 1/2 y squared, plus negative 1/2 y to the negative 2. So y squared over 2 minus 1 over 2y squared. And that gave me y to the 4th minus 1 over 2y squared for my dx dy. So this would be square root of 1 plus y to the 4th minus 1 over 2y squared dy, because we're using those y values. So integral from 2 to 3. And what we're going to do is I'm going to go ahead and multiply this out as a binomial. So this is going to be y to the 8th minus 2y to the 4th plus 1 over 4y to the 4th dy. And then we're going to go ahead and make this all over 4y to the 4th. And so when we do that, we got 4y to the 4th plus y to the 8th minus 2y to the 4th plus 1. And when you do that, you can split this up into 2 separates and also put all your stuff together here. And this actually becomes 2y squared outside the root. So that ends up being a perfect square. So we've got the square root of y to the 4th plus 1 quantity squared over 2y squared dy. And so that square and that square go away. So we end up with y to the 4th plus 1 over 2y squared dy. And since that's a monomial in the denominator, you can make this 1/2 y squared plus 1/2 y to the negative 2. I'm just going to go up here from 2 to 3. So this is going to be 1, I think I'm ready to integrate 1/6 y to the 3rd. And this is going to be minus 1/2 y to the negative 1 from 2 to 3. So 1/6 times 3 to the 3rd, I'm going to say 1 over 2 times 3 minus 1/6 times, I said 2 to the 3rd, 3 to the 3rd there, 2 to the 3rd here, minus 1 over 2 times 2. So we've got 27/6 minus 1/6 minus, this is 8/6 minus 1/4. So 26/6 minus, this is going to have to be 12ths times 2 times 2, 16 times 3 minus 3. So 13/3 minus 13/12. Ooh. So times 4 times 4. 52/12 minus 13/12. 39/12 divided by 3 divided by 3 gives us 13/4. But that's it. Not too bad. You should try your homework.